it seems that I changed the title just because I prepared yesterday evening. In fact, the talk is based on, this is partly based on a joint work with Pevera, Pim, and Duse. So Brent was here on Monday. And in fact, the starting point is a project. Our goal was, is still, to find an analog of what I call the BB. So this is Bovil-Bogomolov decomposition theorem. So for foliations. So I'm not assuming that you know what the foliations here. I mean, on introduction, yes, but I will try to recall a few things about foliations later on. So this was our goal, the starting point. So we failed. So I will present a weak result in this direction. And as usual, when you don't manage to do something, you add your assumptions and you go in a slightly over directions. This is exactly what I did. So to fix the notation, so X will be smooth, projective of dimension over C, and of dimension N. H will be an ample divisor on X, and F will be a regular foliation of rank R, and most of the talk will be codimension 1 foliation, so R will be n minus 1. So and I made an assumption. So suppose that F is H semi-stable. So this happens from time to time. So there are two examples I have in mind. The first one is when F is Hermite-Einstein. And more importantly, the second one is when the first chain class of F is 0. This is related to this, the 3B decomposition. So this is not easy. So this is the easy part of the Kobayashi chain correspondence here. But in this case, this follows from the work by Campana found. Okay, so these are two examples. So in this setting, there is the so-called Bogomolov-Josefian inequality.
So Campana found, you say that like if C1 is 0, then F is...
No, Campana found, okay, so you want the argument. So if it's not semi-stable, you have something of positive slope contained inside. So the maximal destabilizing subshift has to be a foliation. Campana bound tells you that this foliation has to be uniruled. So you have rational curves that are tangent to the foliation. And now, if you have rational curves that are tangent to the foliation, they cannot have C10 here. The reason is if you are tangent to the foliation, the normal bundle is flat on the foliation. So the anti-canonical degree would be 0. And the anti-canonical degree of a covering family of rational curves cannot be 0. So this is Campana bound plus epsilon. So this is the Bogomolov-Josefian inequality. It says that so the rank is C1 squared F minus C. This is the opposite. It's always non-negative. And it turns out that if you impose equality here, this has a strong consequences on the geometry of F or the geometry of X. And let me just take one PRS, which is due to Janke and Radloff. 2013. So this is the special case of a foliation with just one leaf. So F is Tx. So suppose that Tx is semi-stable. And you assume that we have equality here. So C1 of x minus 2 suppose that this is 0, then x is a finite element. Finite element quotient. Of an abelian variety. So this is the kind of result we try to extend. We try to get for foliations. So I will give you later on equivalent conditions for equality in this homological inequality, so that you will understand that this is a very strong assumption on the tangent bundle of x or of equations. This is a really strong assumption. But before, I want to just recall a few things about, let's say this is one, about the foliations. Foliations, and we'll just consider for simplicity Codimension 1 foliation. And we only consider regular Codimension 1 foliations. So what it is? So the regular is the data of an open covering.
So does that follow from the Uhlenbeck-Yarrow theorem?
Sorry?
The consequence of the Uhlenbeck-Yarrow theorem, no?
No. No, the things we have to, what you have to prove is that under this assumption, the canonical class of x is 0. And then, I agree. Yeah, this is the point. Okay. C1 is not 0 here.
But this is not a theorem of foliation, this one. Does it use foliation?
This is a no. But you have to think, you have to have in mind that this is a foliation. Just one thing. But this is the easy case. You will see that the statement is more complicated in the case of codimensional foliations. So this is the data of an open covering. So these are analytic subset, analytic open. And for each UI, you consider nowhere vanishing one form. And there are two conditions. The first one is the integrability condition. So omega wedge the omega I is 0. And the second one is the compatibility condition. So on overlaps, omega I has to be proportional to omega j. Gij here is the unit. So if you have this, you can check immediately that this Gij satisfies the co-cycle condition. So you get a line bundle, which is called N, for normal bundle. And the omega I, they glue together to get a twisted one form with value in N. Okay, so in the end, you can consider the kernel of omega. This is omega. And what you get, this is a subbundle. So this is the nowhere vanishing condition. And this one has to be stable under the Lie bracket. And this condition is the integrability. Okay. So you can also define a foliation to be just a regular foliation, to be a sub-envelope, a stable under the bracket. This is almost equivalent. The important notion here is the notion of leaf. So as soon as you have this integrability condition, you can apply the Frobenius theorem. And in this setting, it says that if x, there is a point in the open UI, there exists local coordinates x, z1, z1, zn1 to zn, such that your form, your one form, is up to a unit, say given by z1. You can change the local one form and assume that it is even given by z1. So the local leaf, so you have some open here, and you have some the chart. So this is this one are called foliated charts. Those two are open in Cn. So Cn, this is C times C and minus 1. This is a Z1 coordinate. And you can consider the level set of the coordinate Z1. And this is straight. You can see the same picture here. And this image of the level sets are called the plaques. Plaques, and you have to think about it as a kind of local leaf. So the main property of these plaques is since omega I is given by dz1, the kernel of the f here exactly, or I mean when you restrict to the plate, corresponds to the tangent shift of the plate. So if you call it L, say L, you see that the main property is the tangent of L. By definition, is exactly the direction. Okay, so the plaques are tangent to the foliation. And this compatibility condition there says that you can glue the picture. So if you have one foliated chart, number one, so you have the picture here, and you can look at the same picture on the other chart, and they have to do. This way, you can define an equivalent relation on X. So you say that 2 points are equivalent if they can be joined by finitely many plaques. And you call the leaf L is a leaf. This is an equivalence class. Okay, so the point here is that the leaves comes with a topology. This is the topology induced by the plaques. We decided these plaques are open on L, and this topology in general is different from the topology induced by Hilbert space. So the topology is much more complicated, and this is even more. And is a complex analytic. So this is the complex structure is again given by the plaques, and you have an immersion defense. But this is not closed. That's the main point. Okay, and with exactly as here, the tangent of L again. Is given by F. Okay, so let's see a few examples that will appear in the theorem. So the first one is the, let's say, daily case. So you consider a smooth morphism. Onto a curve with connected fibers. So to give a foliation, I have to give a twisted one form. So you can consider the pullback of the cotangent. You declare that this guy is the conormal bundle. So this gives you a twisted one form. And by construction, the kernel is exactly the relative tangent. And the leaves are the fibers. So in this particular case, the leaves are algebraic, but in general, this is definitely not the case. So example 2, say we start with an abelian variety or a complex torus. So lambda is a lattice. And you fix a linear projection into C. So this defines by one foliation. So it's given by linear projection, and you see that this foliation is invariant under the action of lambda on C to the N. Okay, so the leaves are the fibers, exactly as in the first case. So if you fix the value of the image, if you apply an element, the value of the image, the fiber is mapped to another fiber by this automorphism. But this implies that the foliation descends. So this is easy to see that you get a foliation. F on A. And not difficult to see that F has trivial tangent bundle. Just look at the vector fields that are tangent to the fibers here. They descend also. So they trivialize the tangent bundle, and the normal bundle is trivial also. This is just a foliation given by a global one form, which is closed. In this particular example, if you choose if the one form is sufficiently general, the leaves are all dense. Okay, so this is a more algebraic approach. And the final example is a bit more interesting. So again, this is a special case. So this is a special case of something called suspension. Suspension of our representation. So you start with now an abelian variety of dimension n-1, and you fix a representation rho from line 1 of A to the automorphism group of P1. So you can replace A by anything else and P1 by anything else. So So now we consider the product Cn minus 1 times P1, and you consider the projection to P1. This is again a foliation. By example 1, you have the fundamental group. You get the fundamental group acting diagonally. So on the first factor, this is just by translation, and you act on P1 through the representation here. And again, this action leaves the foliation invariant. Okay, so this is invariant. Here, the action of P1. This induces a foliation of the quotient. So you get a foliation of X, which is Cn. So this is a particular foliation. So you have a projection to Cn modal to P1 of A. So this is A. This morphism here is a P1 bundle. And it corresponds to the projection onto Cn. So you see that your foliation here is horizontal with respect to this morphism. So in fact, F is everywhere. Well, transverse to phi, and this is what we call a flat Dirac connection. On phi. So flat, this is because F is a foliation.
There is a sort of map to P1 over phi1, but P1 over...
A map?
So this quotient, it maps to P1 quotiented by...
yes, this is the space of leaves, and yeah, this is the space of leaves, and it's much. So the flatness comes from the fact that the foliation is this is the integrability of the foliation, and the Dirac condition is just something you can check. So F induces a splitting. So F is contained in Tx, so induces a splitting of the relative tangent bundle segments. This is the definition of an Dirac condition. And in particular, you see that, again, F is trivial in this example.
So this phi, this P1 bundle, this is like a Gauss theorem, or that's a projectivization of something?
So this is a projectivization of something. Because the point is that, in fact, there are not too many representations of something abelian into P1. So up to conjugation, either you are contained in a torus, or you are unipotent. So if you are contained in a torus, in fact, this variety is just the projectivization of a line bundle, which is flat, plus its dual. And if not, you just consider the extension of a line bundle by itself, which is undecomposable, and you get unipotent case. There are only two possibilities, in fact, in the end. But you can produce more interesting things if you replace P1 and A by something else. Okay, so these are the examples. Ah, yes. So I promised that to give equivalent conditions to the that appears in the theorem by Ranker-Adloff. So this is numerically flat. Numerically, projectively flat. So here, E is a vector bundle. From R. So this is a theorem, and this has been observed or noticed by Nakayama and say Ranker-Adloff. But that should add a long list of names because this is highly non-trivial. And so this goes back to the Narasimhan-Seshadri, Donaldson, Uhlenbeck-Yao, you can add Simpson, and also Demailly, Petan, and Schneider. There are many. So they just almost put everything together. you get this sequence of equivalences. Okay. So there are two sets of equivalences. So the first one, so the first assumption is E and its dual on F. So this is the definition of numerically flat given by Dominique Wittgenstein. Okay, so this is, let's say, this is a starting point. And in their paper, they show that this is equivalent to say that there exists a filtration. Say 0. With quotients K being unitary flat. In particular, induced by representation in a unitary group. So these quotients are polystable. Okay, but the extension is not in general. And if you add Simpson and Abelian correspondence, you can see that this is equivalent to say that H is H semi-stable and flat. So this is for a numerically flat. Now I switch to numerically projectively flat. And the definition, let's say, is this one. So you consider the so-called normalized vector bundle, and you ask for this guy to be numerically flat. So I say that this is a definition of numerically projectively flat. You should have an example in mind of this. Just consider E to be L, so some line bundle to the power R. So this guy is just OX to some power. Okay. So in particular, this vector bundle is always numerically projectively flat. Okay, so just projectively numerically flat means numerically flat in average. But here the C1 is not necessarily 0. So you rescale everything, so C1 is 0.
If the determinant is divisible by R, and then
if the determinant is divisible, this is equivalent to say that E times the square R fold is numerically flat. Okay, and then there is an equivalent condition to that one, so there exists a filtration.
But it seems to me that you can always construct finite covers on which the determinant becomes divisible by R and then work the upset.
No. You have to make the degree has to be sufficiently divisible, no? To be divisible. If the degree is not divisible by R.
I think if you have any line bundle over any projective variety X, you can construct a finite cover X prime on which your line bundle becomes divisible by R.
I don't want finite. I want only a type cover. I mean, I don't want to reduce to the. You cannot reduce to that case. Okay, I agree. This makes sense also. So the filtration with. So this time, the quotients are Hermitian projectively flat. And this is important. First in class of the quotient is exactly the one of C1. So in in average. Okay. Now I come to the third condition. So this is the one that appears in the theorem. This is E is H semi-stable. And C2E minus 1 squared.
So the E and
the E and the E,
they're all the same.
they are all the same, yes. Maybe I forgot the analog of that one, sorry. The analog of this one is H semi-stable. And E is projectively flat. So projectively flat just means that the projectivization of E is flat. So induced by the representation into PGLM. So this is the assumption we are interested in the second theorem, and we will work with this assumption in the first video. So now let me take the first two results.
Does the proof in Janke-Radloff use this for retention?
Sorry?
The proof in Janke-Radloff, do they use this? Or do they do
Yes, you need to have all the info. If there is a 5 condition also. But all these conditions are equivalent to say that the E restricted to any curve is semi-stable. And you need to have all the point of view to conclude. Okay, so the first theorem is exactly what we expect as an analog of the Bovee-Bogomolov decomposition theorem, except that we have an extra assumption. So this one is joined with Georges Pereira, Mike Pim, and Fred Touzé. So any much more general setting, so we may assume that just X is scalar compact. F is regular of rank R, and F is numerically flat. So we would like to just to say that C1 is 0, but unfortunately we cannot. Then we can prove that in fact F is Hermitian flat. So this is equivalent to say that F in fact is a polystable. This is not an interesting part. We can show that any minimal invariant, F invariant subspace, basically an analytic subspace, is a finite étal quotient of complex torus, and we call it the minimal invariant subspace Y, and F of this Y is linear. So linear was the example 2 before, given by a projection. So the typical example of minimal is just to take the Zariski closure of a leaf. In particular, if all the leaves are dense, this is by definition, we say the foliation is minimal. If all the leaves are dense, X itself has to be a particular quotient of an invariant variety. And the BB decomposition is this one. So we can show that there exists a G supplementary to F, so foliation.
When you have the Hermitian flat and then the unitary flat, is the same one?
Yes, I mean, it is a polystable. This is what I want to do. It is direct sum of a unitary flat. Yes, you're right. This is a unitary flat.
So the difference is that here you have the filtration and here you say that it's a direct sum.
This is polystable. Different. Here this is semi-stable, and in this case this is just polystable. So there exists a foliation such that Tx is F plus G, and more importantly, the union side cover of X splits as a product, so C to the R. R is the rank of F times something in such a way that the decomposition we have here leads to the one given by a product, so TCR plus T1. In particular, the leads are uniformized by C to the
Subspace, you mean compact or something?
This one?
No. Any minimal F invariant subspace.
Closed. Closed analytic subspace. Yeah, this is a closed analytic subspace.
So the closure of a leaf.
Yeah. This is one. Closed analytic subspace. So this is why we want to call a weak Bovie-Bogomolov decomposition field. So we expect the same to be true, just under the assumption C1 is equal to 0. So this is not to be true, the codimension is 1, and this is due to Z. So, and there is also some hope to have a similar, something similar in the singular case, but far from this. Okay, so this is the first result, and the second one. I should say that this is in progress. And you will see that not satisfied with this. So, this time I go in a slightly different direction. So I'm not assuming that F has any rank, but I am assuming that it is numerically projectively flat. So I have to put an assumption is that the dimension of C is 4. And I'm assuming that so F is regular, codimension 1, with F numerically projectively flat. Okay, so here the C1 is 0, here C1 is not 0, but the assumption is on the codimension. So then one of the following all. So this is an analog of the Yankel-Radloff theorem in this case. So the first case is the case of the suspension. So that exists P1 bundle structure. So P on X such that with Y a finite eta quotient of an abelian variety. The second case is F is linear. And F is random. Sorry, yes, and F is an arrangement connection. So this is the example we saw. The second one is F is linear up to a finite theta cover. That means that the finite theta cover X is an abelian variety, and on this finite theta cover, your foliation is linear. And the third one, so there exists a diagram here of a C, say gamma X. So this is a finite theta cover. And this here is an abelian scheme over a curve. And because we are interested in the foliation is exactly given the morphism of C. So in particular, in this particular case, the leaves are algebraic. And the fourth one is the foliation isophilia. B2C, no, sorry, so thank you. So we can assume that G of C is at least 2. G is 0 or 1, the fibration is trivial, and we are in the first two cases. If the fibration is isotrivial, this is the product. That's it. In fact, the C1 has to be 0 in this case of the foliation. But if the foliation is not isotrivial, this is the case where the C1 is not 0. So the codal dimension is 1 when the fibration is not isotrivial. But there is no assumption on the isotriviality or not. The only interesting example is when the fibration is not isotrivial, I would say. And the fourth one is something strange. So I tell you exactly all what I know. So the canonical path of X has to be on both. The conormal has to be net. The cotangent of X has to be net as well. So in particular, R is net. And yeah, F is of general type. So that means that the Codera dimension of the determinant of the dual, you have to think of the F as a tangent space and the dual as a cotangent. So the Codera dimension is maximal also. And there is no compact leaf. Okay, so as you can imagine, I don't have any example in case 4, and I suspect that this case does not occur. I can't believe that there are examples. A remark? No example. In case 4, maybe something I should have noticed before. If the dimension is 2, so we have a foliation by curves, and any line bundle is numerically projectively flat. Okay, so this is so there is no assumption. So in dimension 2, this the classification of this object reduces to the classification of a regular foliation by curves. This is due to good enough. And as you can imagine, this is much more complicated. Okay, so I'm not claiming anything in dimension 2, and in dimension 3. I don't know. But this is just a technical condition. At some point in the proof, I have to use that n is at least 4 to conclude something. But I suspect that this is exactly like this. There's no more example. So this is why I say this is in progress. I'm trying to remove this foliation. But I have to say that even in dimension 2, when the surface is of general type and the foliation itself is of general type, the foliation is not well understood. This is the only case in dimension 2 where we don't understand exactly what happens. You agree? We have an example in dimension 2, but we don't know if they are the only ones. Okay. So I don't want to say something on the proof. Just want to present another result that I use in the proof of theorem B. and that I find surprising. This is, say, theorem C. So this is, let's say, propositions, and we will see this is really easy to prove. And it says the following: so that now there is no assumption of the dimension of X, and you consider F regular codimension 1 foliation with normal bundle N. As usual. And the conclusion is that either N is pseudo-effective, or its dual, which is called a conormal bundle, is NF. So the normal bundle of a foliation always has a sign. It's surprising. Okay, so I will give the proof, but before, I'll just say that this is a consequence of theorem C prime. You consider a line model. You suppose that L is contained in a cotangent of X, not assuming that this is a sub-vector. Okay, just a line model containing the cotangent. And I am assuming that, so L squared, so this is not the two torsion, but this is the self-intersection product. So I am assuming that this is 0. Say H4. Okay. So then the same conclusion holds. So then either, so this time this is L is NF, or it dual, you pseudo-effective self.
So the X is a perpendicular as before.
No, projective. You will see why. So the question is, suppose that N is a line model. Where L squared is 0, so as before. Can you say something on that? So is the conclusion always true? Not the conclusion, because NF is too much. Can you expect that L is set or the opposite? I don't know, but I have a proof in this particular case. How much time do I have?
About 10 minutes.
10 minutes. Okay, so the proof. We need two lemmas. So lemma 1, S, I think that S is the surface. So smooth projective, and you take a derivative D, D divided by S, with D squared means 0, and then D or minus D is pseudo-effective. Okay, so this answers the question in dimension 2. And the proof is an exercise. So assume say that BH is non-negative for some unknown. And then you consider D epsilon to be D plus epsilon H. And you compute D epsilon squared. So this is epsilon 2dh plus h epsilon h squared. This is strictly positive. And you compute D epsilon h. which is again, so this is the epsilon h squared. This is again positive. And this is an exercise using Riemann law to see that this condition implies that the epsilon is Q effective. This implies that D itself is a pseudo-effective. Okay, so lemma 2. So S, as before, D squared equal to 0 and D pseudo-effective. Okay, and now suppose that the Codera dimension of D is at most 1, then D is there. Yeah, so the proof. Okay, so D is pseudo-effective, so there is a Zariski-Fujita decomposition. P plus N. So both are effective. Q divisor. This one is nerf. The decomposition is orthogonal. And the matrix Mi and J is negatively finite, where the Ni's are the component of N, or N is 0. Okay? Now you see, you can compute the Codera dimension of P. This is certainly less than the Codera dimension of D, which is less than 1 by assumption. Since P is nerf, follows that P squared has to be 0. Okay, now you compute D squared, which is 0. So this is P squared, which is 0. The penalty gives 0, and you get N squared. Since the matrix is negatively finite, this implies that N is equal to 0. So the only non-trivial ingredient we need is the Buxton-Domain beta bound theorem. So this is the place where we need the projectivity. But I guess the more crucially, proof of theorem C prime. Where is theorem C prime? So suppose that L star is not pseudo-effective. Then you use B Buxton-Domain bound Pétanel. You say that there exists beta birational, x1 smooth, and there exists h1, hn minus 1 ample on x1, such that if you pull back beta, you intersect h1 up to hn minus 1, so you get something positive. There is a star, there is in the end this is positive, but not negative. Blah blah blah. Okay, so now I want to show that L is nerf, so this is to show that beta star is nerf. So take C in X any curve. And use let's say a variation of the Bernoulli theorem. There exist the positive integers k1, kn minus 2 AI, general members of KI, HI, such that C is contained in AI for all I, and you intersect A1, N minus 2 is irreducible and so you reduce to the case of of the dimension 2. So suppose S is smooth for simplicity. And so at this point I have not used the assumption in the theorem. Suppose that S is smooth, so you know that L restricted to S, so this is 0. You know that L restricted to S intersected with H n minus 1. So this is 0. This is positive. So you use lemma 1 that says that L restricted to S is pseudo-effective. And then I claim that since these are general elements, may assume that the natural mark from L to omega 1x restricted to S, so you pull it back, you go to omega 1 x1 restricted to S, and you go to omega 1 s1, you may assume that this is non-zero. And then you use Bogomolov-Somese vanishing. You have something contained, line model containing a cotangent of a smooth projective, so the smooth variety. Its Codera dimension is at most the exponent here. This one plus this one. So that L is enough. I think I stop here.